Okay, so now we're doing question 7. All right, so a student carried out an experiment to determine the value of the equilibrium constant Kc for the esterification reaction between ethanoic acid and ethanol. And then it gives us an equilibrium equation. Ethanoic acid plus ethanol goes to ethyl ethanoate plus water. And then they ask us to write an equation for this reaction. So they've given us a word equation. What they're asking us to do is to write a symbol equation, which is fairly straightforward because they've given us fairly straightforward compounds. So ethanoic acid, CH3COOH, and then ethanol, which you've done many, many times, CH3CH2, oops, make a mistake like that, OH, and then we must do our equilibrium sign, and then ethyl ethanoate. So it's an ester and it's a ethanoate, so it's going to be CH3COO. So there's the ester group, COO, and the ethanoate part is the CH3C, because it's because this carbon here is the carbon, that's the carbonyl carbon, and then we've got CH2, CH3 plus H2O. So what I'll do is I'll just draw this ester structure so that you can, oops, it would help if I got it right, wouldn't it? So the ethyl part is the part bonded to the singly bonded oxygen is that part, and the ethanoate is that part. Okay. Right, so again, if you're still feeling a little uncertain about naming esters, then it is a very straightforward thing to go over. So at the very least, that's something you need to go over. And if you need any help with that, just let me know. So we've got to draw the skeletal formula of ethyl ethanoate, and our life is made easier if we have correctly written the equation, because we're drawing a structural formula for this substance here. That's what we're trying to draw the structural formula for. So let's do it in that order. Let's do it in that CH3COO, CH2, CH3 order. So if I do that, that is the bit that I've got in green. So I've got CH3, and then that's my carbonyl. Then I've got it bonded to the oxygen. I'm going down to the oxygen, and then I have got that. So so that is my CH3, COO, CH2, CH3. Okay, that is if you compare that then with the formula I've got up in part A, I've written it in exactly the same order. Okay, the student used a small amount of concentrated sulfuric acid as a catalyst to increase the rate of the reaction. So state in general terms how a catalyst works. So one of the things, or the way a catalyst works, is that it provides an alternative. And I know a lot of you will say pathway, and you may get away with that, and I've marked that correct, or an alternative route. But I think we can be a little bit more sophisticated than that, and that's what we should be trying to do. So what it's actually providing is an alternative mechanism. All right, so that is the different route. The mechanism is the different route or the different pathway, but it's just making it a little bit clearer. And a consequence of that is that this alternative mechanism has a lower activation energy. So 1 mark for saying there's an alternative mechanism, and 1 mark for saying that alternative mechanism has a lower activation energy. So that's how a catalyst, any catalyst works in general terms. So you're going to do catalysts in transition metals, and that will be, in effect, an alternative mechanism. All right, so now we come to this question, and I'm not going to lie, this is probably, at least for the number of marks and the time it takes to answer, this is, I think, one of the hardest questions I've seen in the new specification. It was in a specimen paper. They haven't, since the specimen papers, they haven't done anything quite as difficult as this, although they have done a question in an AS paper which had a similar method, at least anyway, of solving. So it's an important one in terms of the principle behind it, even if this very question is perhaps a little too much, or a little bit, is asking a little too much in the time that really would be allowed in an exam question. The first thing is, we are still talking about the same reaction that we were talking about at the beginning of this question. So we're reacting ethanoic acid and ethanol, and we're going to get our ethyl ethanoate and water. And they've given us the word equation, right? So, even with a little bit of, doubts on that or getting things wrong in those first few questions, we still have the information, or we still have a lot of the information that we need. So I think, when you've got, you've been given moles of ethanol and you've been given moles of ethanoic acid, you've also, and this is slightly a little bit confusing, but you've been given the moles of the sulfuric acid. But we've just had in the previous question, they've just told us that this small amount of concentrated sulfuric acid was a catalyst. All right, so they've reminded us of that. So one of the things that we should do is we should just remind ourselves here that this is acting as a catalyst, which means that it's not used up, and therefore the way we should consider it is that that number of moles is constant. Okay, because if it's not being used up, even regenerated, but let's put constant number of moles. So that is not changing. Okay. So the mixture was left for 1 week to reach equilibrium. So we're assuming it's reached equilibrium. The equilibrium reaction was stopped by adding the mixture to water, and then they've given us a Kc value, that the temperature of whatever the experiment took at. So all they're saying is they're making it clear that Kc is dependent on temperature, and they're just giving a Kc value for whatever temperature this was at. And then it says calculate the volume of 0.044 moles per decimeter cubed of sodium hydroxide solution required to completely react with the acids. So that's an interesting thing to make a note of, is the fact that it's plural acids in the equilibrium mixture. So I think if you're given moles, you're given a Kc value, there's a few steps to follow here. It is a 6-mark question, but I think one of the first things you should do is draw an ICE table. Okay, and if that doesn't mean anything to you, then it's very important that you follow this video carefully. So let's write the equilibrium equation. So it was ethanoic acid plus ethanol goes to ester, ethyl ethanoate plus water. Okay, and then our ice, so this is standing for initial, so that's our initial moles. C stands for change, and then we've got equilibrium, so the moles at equilibrium. Okay. Right, so what are we given? We are given ethanol, the initial, so that is 0.0435. and we are given the same for ethanoic acid, 0.0435. And then the initial moles of the right-hand side have got to be 0 because the reaction hasn't taken place, hasn't started. The initial is, you've got them essentially almost your ethanoic acid and ethanol in two separate containers. So you haven't actually, the reaction hasn't taken place yet. Now, normally you're given one of the products at equilibrium, right? You're given the value for one of the products at equilibrium. And then you then use that to complete your table. But when one thing to remember, I haven't done that, but one thing to remember is when you are given one of the equilibrium, one of the products and its moles at equilibrium, you construct your table so that you can work out Kc. But we're actually given Kc. So this time our unknown is something a little bit different. Now, the other thing I'm just going to add, and actually I'm just going to move this down a little bit, is, oops, I don't want that pink there to go. So I'm just going to put the molar ratios above it. I'm just going to keep it in green because otherwise I think my colour. So when I did my reaction, it was a 1 to 1 to 1 to 1 ratio. That's important, right? So you should do that for your ice table as well, because when you're doing your looking at trying to fill in the rest of the table, you need to know your molar ratios. That's very important. Okay, so we don't know how much ethyl ethanoate is going to be produced or how much water. So I'm going to let it equal Y. So Y moles of ethyl ethanoate is produced, which means I get a change of plus Y. And my ratio of ethyl ethanoate to water, so if I make Y moles of ethyl ethanoate, I must also make Y moles of water. So that change is also plus Y. If I go back to the left-hand side and I go to my ethanoic acid, it's a 1-to-1 ratio between ethanoic acid and ethyl ethanoate. So if my change of ethyl ethanoate is plus Y, my change in ethanoic acid must be minus Y. And that means that my equilibrium mixture, or in my equilibrium mixture, there are 0.0435 minus Y moles. And ethanol, 1-to-1 ratio, so that must also be a change in minus Y, so that must also be 0.0435 minus Y. So this using having an unknown like this doesn't crop up very often. You have done questions on this, but not very many of them. And then, so what tends to happen is you do them, you don't really maybe quite get it, it's explained to you, fingers crossed you get it, and then you forget about it. You forget because you don't see it again for ages. So what you've got to do with a question like this is when it comes around and your teacher says this is the type of question that can occasionally come up, you have to store it. You almost want to have somewhere in your filing or something a collection of whatever you want to call them, interesting questions or different questions or unusual questions, but you want to collect them together, because when you're doing your revision you need to make sure you're reminded of those questions, because familiarity with this type of question is going to make a massive difference to your ability to recognize when it's applicable and therefore to actually answer it. Okay, if we're thinking about strategies, so we're actually now going to start the question properly. If we're thinking about strategies, if you have any equilibrium question, if you just simply write the equilibrium expression for that equation, for that reaction, you will definitely, almost definitely, but I've never not seen it, which is why I'm saying definitely, you will definitely get 1 mark. And that is not a difficult thing to do, right? I appreciate there's another 5 marks, but every mark is going to count. Every mark is going to matter. So let's write our Kc expression. Now it's our products over our reactants, and they are to the power of whatever their molar ratio is. And I've got my ethyl ethanoate. And I've got my water. They are over, let's make that a straight line. They are over the ethanoic acid. And the ethanol. So that's 1 mark already. And now I've done, I mean, this is also about strategy, exam strategy. I've written my ICE table because that's what I'm pretty sure I was going to have to do, because this is an equilibrium question where I'm having to calculate something. I've written my KC expression, and now because of my ICE table, I have the terms to put into my KC expression. Okay, so I've set myself up to be able to answer this question. So KC is 4.07. Just check that, yeah. So KC is 4.07. And then that equals, and then I've got Y times Y over 0.0435 minus Y again. Now the next step here is quite important. Your life is going to be much easier if you now write it like this, because I think you're going to see much more easily. So I've just multiplied those two. I've just said, look, I've got Y times Y, so it's Y squared, and I've got 0.0435 minus Y times 0.0435 minus Y. So that's 0.0435 minus Y all squared, right? Now, you could try and, you can do like multiply both sides by the right-hand denominator and so on, and you could go down the whole quadratic equation route. But honestly, you can get the right answer, obviously, clearly, but you are more likely to make a mistake, or more likely to go awry, or more likely to forget something, or whatever. A much, much simpler way now is to square root both sides. So if I square root the left-hand side, I get root 4.07 over Y, so that's the square root of Y squared, over 0.0435 minus Y. And now I want to simplify it, right? So now I want to get it in terms of Y. So it's going to be about keeping things in your calculator as well. So I'm the square root of 4.07 is 2.017. So I'm going to write on here 2.02, but I've kept it in my calculator. And then that is going to be multiplying, because I'm going to multiply both sides by 0.0435 minus Y. Okay, then I expand the brackets. So I'm going to get so now I've got 0.0878 minus 2.02 Y equals Y. So that means 0.0878 equals 3.02 Y. Therefore, Y equals 0.0291 moles. Oh yes, sorry, just while we're here, actually, one of the things that might have thrown you is the fact that you weren't given a volume. because obviously these square brackets in the Kc expression are concentration, and we were given and we calculated in our ICE table moles. So really we should be dividing moles by volume to get concentration. If you ever spot, or if you ever notice in the information you're given that you haven't been given volume and you think that you should have been, because that's how you would work out concentration, just look again at the reaction equation, and if the total number of moles is equal on both sides of the equation, so in this equation it was 2 moles on the left and 2 moles on the right, what that means is that the volumes would have cancelled out, and so that the volumes can actually be ignored. So if the total number of moles on both sides of an equilibrium equation are the same, that's the total moles, then the volumes will cancel out, and so you don't actually need to use volume. So now we've got Y. What that's telling us is how much ethyl ethanoate we've used. We made. So we've made that much ethyl ethanoate, we've made that much water, but it also tells us how much ethanoic acid we've used. And if you think about what we're ultimately doing to check this reaction, if we just go back, it says calculate the volume of 0.400 moles per decimeter cubed sodium hydroxide solution required to react completely with the acids in the equilibrium mixture. So in the equilibrium mixture, the amount of ethanoic acid is 0.0435 minus Y. So therefore, moles of ethanoic acid at equilibrium equals 0.0435 minus Y, 291. Okay, do you know what I'm actually going to do? Right, I'm just going to shift everything to the left so I've got a bit more space. I would have been in the real thing. I would see more clearly how much space I'd used up, but I didn't see that anyway. So that equals 0.0144 moles. So when we add our sodium hydroxide, it's going to be reacting with that number of moles of ethanoic acid. Now, remind ourselves again that in that part of the question, calculate the volume required to react completely with the acids. So the main acid is ethanoic acid, but we also have the sulfuric acid. Now, we said that is a constant number of moles. Now, the other thing I should have just pointed out is H2SO4 releases 2 H plus ions for every 1 H2SO4. So therefore, the number of moles of H plus ions is 1.00 times 10 to the minus 3 mole of H plus ions, right? And that's what we're reacting with when we do the when we're trying to calculate the volume of sodium hydroxide. It's the volume of sodium hydroxide, or ratio of sodium hydroxide to H plus ions is 1:1. So we then need to add, also then what we've got going on here, so therefore total moles of acid, or of acids I should say, maybe make it clearer for us now, equals our ethanoic acid number of moles, which is 0.0144, plus our moles of H plus ions from the H2SO4, so it's 1.00 times 10 to the minus 3 equals, and that is 0.0154 moles of H plus ions in total. So that's 0.0144 of ethanoic acid, which we worked out from our Kc expression, or that allowed us to work it out, plus the the 1.00 times 10 to the minus 3 moles of H plus ions from the sulfuric acid. Okay, so let's go back. So we were given the concentration of sodium hydroxide. Okay. So H plus OH minus goes to H2O, right? That's our neutralization reaction. And it's a 1-to-1 ratio. And we know that we now know that we have 0.0154 moles of the H plus ion. So that means we will need 0.0154 moles of the OH minus ions. So concentration equals moles over volume, dm cubed. So therefore, volume equals moles over concentration. And the number of moles is 0.0154. And the concentration is 0.400. So that equals 0.0385 decimeters cubed, but they want the answer in centimeters cubed. So we times it by 1,000. And so there we go. Now that is a tricky question. So let me just talk you through it again. So I'm going to try and show all of the working out here. Okay, so we were talking about the same reaction that was given right at the beginning of the question. And we were given moles, initial moles of ethanoic acid and initial moles of ethanol. And we were also given a Kc value. And then we were being asked, so we were having to make a connection here, we were being asked to calculate the volume of sodium hydroxide needed, given that concentration that would react completely with the acids in the equilibrium mixture. So here with the acids, we needed to recognize that it was whatever was left of ethanoic acid plus the catalyst, which sort of stayed constant, plus the hydrogen ions from the sulfuric acid catalyst. So we needed to write an ice table. So it helps to rewrite the equation because it wasn't written out for us on this particular part. It's important to put the molar ratios because that's going to be important when we're looking at the change when we do our ice table. We do an ice table, so it's initial moles, change in moles, and then moles at equilibrium. We were given ethanoic acid, we were given ethanol at initial. We know that the products must be 0, and then we weren't given anything else. So we let Y equal the number of moles of ethyl ethanoate, which meant that it was the same number of moles of water because it was a 1-to-1 ratio. That meant the change in ethyl ethanoate was plus Y and for water plus Y. So then when we thought about the change for ethanoic acid, again, like you see the whole thing is 1-to-1 to 1-to-1. So a change in plus Y on the right means a change of minus Y on the left. So that meant we could write an equilibrium, a number of moles at equilibrium. So it was initial minus change, initial plus change, but so minus Y, initial minus Y. And then we wrote a Kc expression because you should always do that when you're having to use Kc and you're using data like moles or concentration, because that is going to be a mark. That is 1 mark. Now, this is concentration, and these are moles. But because we have the same total number of moles on the left is 2 and the total number of moles on the right is 2, because they're the same, what happens is volumes cancel out. So maybe I should show you that. So what can I write it? If I do Kc equals, and if I just write mole over volume, and it's, to the power of 1, and that's mole over volume, because, you can see these square brackets as the power of 1, and that's mole over volume, and that's mole over volume, and the volume is the total volume of the mixture, right? So the moles can be different, of course, but the volumes are all the same. They cancel out, which is why we could then write our Kc expression where we knew the value of Kc because they gave it to us. We knew the equilibrium moles of the ester and the water, and the same with the ethanoic acid and the ethanol. This was a very important way of then writing that, because having them both clearly squared made life a lot easier, because then what we did is we square rooted everything. Now you could go on and have a quadratic equation. It's more complicated. It should still give you the same answer, but you are more likely to make a mistake, no question. So it's going from here to here. That is the key bit, really. I mean, assuming also you've done that, of course. But people can go wrong here. But if you can go to that point, then it's a case of then just simplifying everything, working out y. So y is that. Remembering y was the number of moles of ester at equilibrium water. But the question was about how much sodium hydroxide was needed to neutralize the acids, and one of them is ethanoic acid. So we had to remember that we needed to subtract y from the initial ethanoic acid to get the moles of ethanoic acid at equilibrium. And then we had to remember, so it is hard, right? There's no question that this is a hard question. We had to remember that we were talking about acids because we had the sulfuric acid. So that's our moles of ethanoic at equilibrium, and that is our moles of H+ ions from our sulfuric acid. So you had to remember that sulfuric acid was diprotic. Again, easy places to slip up on, but you'd lose a mark if you made that sort of mistake. So now we have the moles of H+ ions that are in the equilibrium mixture. We look at our neutralization equation. So the number of moles of H+ ions to the number of moles of OH- ions needed is 1 to 1. So if we know the number of moles of H+ ions, we know the number of moles that we need of the OH- ions. Remember, concentration is moles per decimeter cubed, so it's moles over volume. So rearrange it so we've got volume. That's the moles of OH- we need. That's the concentration of the sodium hydroxide that we have. We get the volume in decimeters cubed, and then we realize that they want it in centimeters cubed, so we multiply it by 1,000. And yeah, hopefully by going through that question twice, I hope going through it that second time has helped a lot. But ask if you've got any questions. And honestly, that probably is the hardest, or joint hardest, or whatever, sort of calculative question I've seen in any of the new spec papers, and it was a specimen paper. Okay, and then this question here. So suggest how the student could check the mixture had reached equilibrium after 1 week. So one thing you've got to if you're going to check that it's reached equilibrium, what that means is you've got to check it's no longer changing, which means you have to test it more than once. Okay, so if you test it once, you don't know that it's not continuing to change. So you could write test more than once, but test several samples. Now, you could argue that it's implicit that you're doing this after 1 week, but it probably doesn't do any harm to spell that out. Test several samples with at least one of these should how do we phrase it? So with at least one of these or at least one tested after a week. Okay. So I would say they should all be tested after a week, really, because then you definitely know. But you need to see, basically you need to see it's not changing. Okay, so you keep testing it until it's not changing. And then you need to spell that out. So check that the result has not changed. So each one of the tests that you would be doing based on this method would have been a titration that you calculate. You know, so that calculation you just did was like the maths, if you like, behind the test. So basically, the way that they were testing whether this had reached equilibrium was to see whether the concentration of acids was continuing to change, in which case it would be the ethanoic acid that was continuing to change. And if it was continuing to change, then it wasn't at equilibrium. The mixture wasn't at equilibrium. But if the ethanoic acid or the volume needed of sodium hydroxide was 38.5, and then the next time you tested it, it was 38.5 centimeters cubed, then you'd know that equilibrium had been reached. So I mean, that was a tough one. I hope that made sense. You might need to look back over it a few times. If you've got any questions, again, please ask me.